Quantum Foam,
Episode 45, Kinematics, Part 2.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
Greetings and salutations. This is Episode 45, Kinematics, Part 2 of Quantum Foam. Let's get back to acceleration. So, the final mathematical quantity discussed is acceleration. Acceleration has a meaning much different than the meaning associated with it by sports announcers and other individuals. The definition of acceleration is a vector quantity that is defined as the rate at which an object changes its velocity. These can be described in formulas that we may or may not get to.
I think it is a good idea to use equations right here on set.
An object is accelerating if it is changing its velocity. So, sports announcers will occasionally say that a person is accelerating if he or she is moving fast, yet acceleration has nothing to do with going fast, technically. A person can be found very fast and still not be accelerating, technically. Acceleration has to do with changing how fast an object moves. If an object is not changing its velocity, then the object is not accelerating, so it could be going at a steady speed.
The equation for velocity is v equals v sub 0 plus a times t.
Show them the data that you have right there.
The data at the right of this diagram I'm looking at here is representative of a northward moving accelerating object. The velocity is changing over the course of time. In fact, the velocity is changing by a constant amount. In fact, 10 meters per second in each second of time. In fact, anytime an object's velocity is changing, the object is said to be accelerating. It has an acceleration. Going around in a circle is constantly accelerating. If you're going around a perfectly round track. It's funny because tracks are actually oval, so there's long stretches where they do the 100-meter dash where you're going straight, at which point you may not be accelerating if you're running at a current steady speed. We go over the meaning of constant acceleration. This is a special case. Sometimes an accelerating object will change its velocity by the same amount each second, as I was saying.
Constant acceleration is reminiscent of gravity.
The data table shows an object changing its velocity by 10 meters per second in each consecutive second, one after another. This is referred to as a constant acceleration, since the velocity is changing by a constant amount each second. An object with a constant acceleration should not be confused with an object with constant velocity. Don't be fooled! If an object is changing its velocity, whether by a constant amount or varying amount, then it is said to be accelerating. Don't be fooled! Don't be fooled! Don't be fooled! Don't be fooled! So it could be constant or varying, and it be accelerating. And an object with constant velocity is not accelerating. That data table depicts motions of objects with a constant acceleration and changing acceleration. And in this diagram, each object has a changing velocity. Since accelerating objects are constantly changing their velocity, one can say that the distance traveled per time is actually not a constant value. A falling object, for instance, usually accelerates as it falls due to gravity, 9.8 meters per second squared, near the surface of the Earth. If we were to observe the motion of a free-falling object, this is called free-fall motion. This is stuff we can get into if we get to it. We would observe that the object averages a velocity of approximately 5 meters per second in the first second, approximately 15 meters per second in the second, and approximately 25 meters per second in the third second of interval. Then approximately 35 meters per second in the fourth second interval, etc., etc. our free-falling object would be constantly accelerating, given the table that I just described. Given these average velocity values during each consecutive 1-second time interval, we could say that the object would fall 5 meters in the first second, 15 meters in the second, for a total of 20 meters, then 25 meters in the third second, for a total of 45 meters, 35 meters in the fourth second, for a total of 80 meters after 4 seconds. These numbers are summarized in a table. I basically described the table for you, so I don't need to read them again. Essentially, it's going faster in each consecutive second. And these values are approximately listed. So the speedometer is an approximation, the instantaneous reading of the speed. So this discussion illustrates what we call a free-falling object accelerating at a constant rate and how much it will cover in each consecutive second. Further analysis of the first and last columns of the data reveal that there's a square relationship between the total distance traveled and the time of travel for an object, starting from rest and moving with constant acceleration. The total distance traveled is directly proportional to the square of time. This is a unique factor. As such, if an object travels for twice the time, it will cover 4 times the distance, 2 squared.
This is the case based on the standard kinematic equations. We don't need to go into too much detail about the specific formulas. We are grasping the concepts.
The total distance traveled after 2 seconds is 4 times the total distance traveled after 1 second. If an object travels for 3 times the time, then it will cover 9 times, 3 squared, the distance. The distance traveled after 3 seconds is 9 times the distance traveled after 1 second. Finally, if an object travels for 4 times the time, then it will cover 16 times the distance, 4 squared. The distance traveled after 4 seconds is 16 times the distance traveled after 1 second, and so on and so forth in that example. For objects with a constant acceleration, the distance of travel is directionally proportional to the square of the time of travel. That is what is important with this distinction in that example.
As I was attempting to tell you last episode, I have some differential equations that I wanted you to look at.
1 second here.
Some of these are time sensitive.
I gotta get back to Newton.
It involves some stochastic differential equations modeling the time-varying nature of the fading channels in our faster-than-light communication experiment.
Yeah, I'll get to it.
I can't wait. Thanks.
Okay,
Good.
thank you.
Alrighty.
Briefly, there's an airplane. Just a second.
I really want to get to those equations.
I'm busy, Newton. I'm at work still. We'll get back to it. Digression. So, calculating the average acceleration. The average acceleration is of an object over an interval of time. It is given with this formula. A equals v sub f minus v sub I all over t. Final velocity minus initial velocity. Basically, A equals v2 minus v1 over t. V sub f is the final velocity. V sub I is the initial velocity. You can either use v sub f or v sub 2, and you could use either v sub I or v sub 1. The notation is not important, but the concepts given by the formula are. Keep that in mind. And t is the time taken for the change in velocity. Keep that in mind. The result is expressed in meters per second squared when talking with something dealing with meters. This equation can be used to calculate the acceleration of objects whose motion is depicted by the velocity time data table that you can make when you're solving a problem if they give it to you. The velocity time data in the table shows that the object has an acceleration of 10 meters per second in this example. 10 meters per second is the same thing as 10 meters per second squared. The calculation can be shown when dealing with these problems. Acceleration values are expressed in units of velocity per time. So, a couple examples. Typical acceleration units include things such as meters per second, miles per hour per second, kilometers per hour per second, or meters per second squared. So, we're aiming towards beginning physics students here, but not very many people understand physics. It's quite a complicated subject. That's why I'm doing computational physics, because the physics of materials and relativity and string theory and all this stuff gets so complicated that how can one person do it? I'm doing a brief of all of these, and hopefully I'll be getting to some depth as well, but I'm mostly briefly going over these topics. So they're aimed at beginning physics students, but you got to know calculus for this in college. So most people don't really know calculus. It's pretty complicated math. It's easy to those who understand math, but they had to learn it at some point. Maybe it was easy learning in the beginning, maybe it was hard. These are focusing at beginning physics students. These units may seem a little awkward, yet they are very reasonable units when you begin to consider the definition and equation for acceleration. It makes sense. We all understand meters per second squared. It's kind of like miles per hour, right? But it's in meters. And we can do some dimensional analysis, changing back and forth by saying 1 mile is, I think, 1,600 meters. Let me check that.
I got you.
This says 1,609.344 to be precise.
Boom.
Since acceleration is a velocity over time, the units on acceleration are velocity units divided by time units. So that's where you get meters per second or miles per hour per second. The meters per second unit can also be mathematically simplified to meters per second squared. That is one that we can understand. So that is the same thing as meters per second, because when you do a divide twice, you do it times on the bottom fraction, and it comes out to be meters per second squared. Next, the direction of the acceleration vector. Since acceleration is a vector quantity, it has a direction associated with it. The direction of the acceleration vector depends on two things: whether the object is speeding up or slowing down, or whether the object is moving in the positive or negative direction, let's say on a Cartesian graph, an XY graph. The general principle for determining the acceleration is if an object is slowing down, then its acceleration is in the opposite direction of its motion. So we usually give a solution to a problem with a graph that has a positive motion of direction. So it would be moving from the left side of the paper or screen to the right side, and that would be positive. It could be going the other direction, and then we just change the grid to viewing the vantage point in the other direction. If it slows down, it's intuitive that the acceleration is negative. That's the idea. Since acceleration is a vector quantity, it has a direction associated with it. Keep that in mind. But I want to at least finish the acceleration section. We went over an introduction, we went into scalars and vectors, then distance and displacement, then speed and velocity, and now acceleration. Acceleration is a vector quantity that is defined by the rate at which the object changes its velocity. An object is accelerating if it's changing its velocity. Keep that in mind. So we were talking about the direction of the acceleration vector, basically the slowing down in the negative direction. This principle can be applied to determine whether the sign of the acceleration is an object. An object is positive or negative, right or left, up or down, etc. We have a couple data tables here. The specifics are not necessarily important, but the determinations made from them is that in each case, the acceleration of the object is in the positive direction. In the first example, the object is moving in the positive direction and is speeding up. When an object is speeding up, the acceleration is the same direction as the velocity. Thus, this object has a positive acceleration. In the next example, the object is moving in the negative direction. For example, it has a negative velocity and is slowing down. According to our general principle, when an object is slowing down, the acceleration is in the opposite direction of the velocity. That's just generally what we do. It makes sense to do it that way. It's intuitive, but you can make your grid any way you want in physics, whether it be a 2D grid, a 3D grid, or some other grid, a grid lattice box, string theory membrane, whatever it is. I'd like to go back into some of that later too, but we got to get back to this. So in that last example, the object also has a positive acceleration, even if it's going in the other direction. There's other examples we could go in with that change positive and negative directions to determine the distinction between different possibilities, but we need to move on here with some other subject matter.
It is important to be able to see a visual representation of the physics being examined.
That is quite true.
So we got it down to acceleration. Next, we are going over an introduction to diagrams. These are very important throughout physics. Diagrams, vector diagrams. There is a persistent appeal to your ability to represent physical concepts in a visual manner. We will quickly notice that this effort to provide visual representation of physical concepts permeates much of the discussion in this physics lesson.
There are so many grid boxes we can make up. Calabi-Yau manifolds are quite the subject to discuss.
String theory was not really around during my last days in the 1950s.
Not really my cup of tea either, but isn't it about time for the midpoint?
But let's take that midpoint.
Hello, I'm Dr. Stephen Hawking.
And I am Sir Isaac Newton.
I am Albert Einstein.
And last but not least, I am Dr. Hezekiah Paul Smith. This is the midpoint of episode 45, Kinematics, part 2 of Quantum Foam. Let's get back to the show. Here we go again for the second half. Permeates. The world that we study in physics is a physical world, a world that we can see. And if we can see it, we certainly ought to visualize it. If we seek to understand it, then that understanding ought to involve visual representations. So as you continue your pursuit of physics understanding, always be mindful of our abilities or lack of ability to visually represent it. We need to know if we can put these physics problems into workable visual representations of before, during, and after an event. Monitor your study and learning habits. This is for the physics students. Ask if your knowledge has become abstracted to a series of vocabulary words that have, at least in our own minds, no relation to the physical world which it seeks to describe. Our understanding of physics should be intimately tied to the physical world as demonstrated by these visual images. Like the study of all of physics, our study of 1D kinematics will be concerned with the multiple means by which the motion of objects can be represented. Such means include the use of words, the use of graphs, the use of numbers, the use of equations, and the use of diagrams. We focus on the use of diagrams to describe motion. Diagrams. We have a vector diagram. Behold. By cultivating your visualization skills early in this lesson, we're going to spend some time seeking to connect the visuals and graphics with words and the physical reality. We're going to read a problem that has words and numbers in it, and then we can put it into a diagram. We have to make connections. So there's a PT graph. We're going to go over the meaning of the shape of this graph and the meaning of the slope for this graph.
A position time graph.
And then we'll be able to determine the slope on a PT graph. Contrasting a constant and a changing velocity. To begin, consider a car moving with a constant rightward velocity of, say, 10 meters per second. If the position time data for such a car were graphed, we could put it on a Cartesian graph that describes this motion. Note that a motion described as a constant positive velocity results in a line of constant and positive slope when plotted as a position time graph.
Constant speed is represented by a straight segment on the PT graph.
Now consider a car moving with a rightward changing velocity. That is, a car that is moving rightward but speeding up or accelerating. If the position time data for such a car were graphed, then the resulting graph would look like a certain motion.
A position time graph for a turning car will show a change in direction, typically represented by a curve or a change in slope.
Note that a motion described as a changing positive velocity results in a line of changing and positive slope when plotted as a position time graph. The position versus time graphs for the two types of motion, constant velocity and changing velocity, can be depicted separately. as I just described.
A straight line and a curved line, respectively.
The importance of slope. The shapes of the position versus time graphs for these two basic types of motion, constant velocity motion and accelerated motion, i.e. changing velocity, reveal an important principle. The principle is that the slope of the line on a position time graph reveals useful information about the velocity of the object. It is often said, as the slope goes, so goes the velocity. Whatever characteristics the velocity has, the slope will exhibit the same, and vice versa. If the velocity is constant, then the slope is constant, or a straight line. If the velocity is changing, then the slope is changing, a curved line. If the velocity is positive, then the slope is positive, basically moving upwards and to the right. This very principle can be extended to any motion conceivable. We can put these problems on these graphs and see what they look like. You should probably just know what these look like right off the bat. Next, representing an accelerated motion. As a final application to this principle of slope, consider the two graphs as I described them. Both graphs show plotted points forming a curved line. Curved lines have changing slope. They may start with a very small slope and begin carving sharply, either upwards or downwards, towards a large slope. In either case, the curved line of changing slope is a sign of accelerated motion, changing velocity. Applying the principle of slope to the graphs, here, one would conclude that the object depicted by the graph is moving with a negative velocity, since the slope is negative on this graph. Furthermore, the object is starting with a small velocity. The slope starts out with a small slope and finishes with a large velocity. The slope becomes larger. Rise over run is the slope. That would mean that this object is moving in the negative direction and speeding up. The small velocity turns into a larger velocity. This is an example of negative acceleration, moving in the negative direction and speeding up. This next graph on the right also depicts an object with negative velocity, since there is a negative slope. The object begins with a high velocity, the slope is initially large, and finishes with a small velocity, since the slope becomes smaller. So this object is moving in a negative direction and slowing down. This is an example of positive acceleration. So the principle of slope is an incredibly useful principle for extracting relevant information about the motion of objects as described by their position versus time graph. Once you've practiced the principle a few times, it becomes very natural. It is a very natural way of analyzing position time graphs. Next, we go over the meaning of shape for a VT graph. There's the slope, there's relating shape to the motion for VT graphs, and there's the area under the curve of a VT graph.
The area under the curve of a velocity time graph represents the displacement or distance traveled by an object. This area can be calculated using geometric formulas depending on the shape formed by the graph, such as triangles or rectangles.
Our study of 1D kinematics is what we're doing. Constant velocity versus changing velocity. What we're looking at now, though, is the importance of slope. The shapes of the velocity versus time graphs for these two basic types of motion, constant velocity motion and accelerated motion, i.e. changing velocity, reveal an important principle. The principle is that the slope of the line on a velocity time graph reveals useful information about the acceleration of the object. If the acceleration is 0, then the slope is 0, i.e. a horizontal line. If the acceleration is positive, then the slope is positive, i.e. an upward sloping line. If the acceleration is negative, then the slope is negative, i.e. a downward sloping line. This very principle can be extended to any type of motion. So is there a positive velocity or a negative velocity? The answers to these questions hinge on one's ability to read the graph. Since the graph is a velocity time graph, the velocity would be positive whenever the line lies in the positive region above the x-axis of the graph. Similarly, the velocity would be negative whenever the line lies in the negative region below the x-axis of the graph. As we learned before, a positive velocity means the object is moving in the positive direction, and a negative velocity means the object is moving in the negative direction. So one knows an object is moving in the positive direction if the line is located in the positive region of the graph, the upper right corner of a Cartesian graph, whether it is sloping up or sloping down. And one knows that an object is moving in the negative direction if the line is located in the negative region of the graph, whether it is sloping up or sloping down. And finally, if a line crosses over the x-axis from the positive region to the negative region of the graph, graph or vice versa, then this determines that the object has changed directions. Speeding up versus slowing down. Now, how can one tell if the object is speeding up or slowing down? Speeding up means that the magnitude or numerical value of the velocity is getting large. For instance, an object with a velocity from 3 meters per second to 9 meters per second is speeding up. Similarly, an object with a velocity changing from negative 3 meters per second to negative 9 meters per second is also speeding up. In each case, the magnitude of the velocity, the number itself, not the sign or direction, is increasing, the scalar value. The speed is getting bigger. Given this fact, one would believe that an object is speeding up if the line on the velocity time graph is changing from near the zero velocity point to a location further away from the zero velocity point. That is, if the line is getting further away from the x-axis, which is the zero velocity point, then the object is speeding up. Conversely, if the line is approaching the x-axis, then the object is slowing down. We mentioned earlier about free falling motion. This would be acceleration of gravity. Representing free fall by graphs is what we can get into, how fast and how far.
I was thinking around on the internet earlier and I came across these position and velocity time graphs, and the image mentioned that it was for 8th grade science. I'm glad they are teaching this stuff earlier on in an individual's academic studies.
And last, the big misconception.
This misconception undoubtedly has to do with Galileo's first experiments at the Leaning Tower of Pisa.
We'll just briefly go over this, and then we will come to a close. We are getting close to the end of our second episode. A free-falling object is an object that is falling under the sole influence of gravity. Any object that is being acted upon only by the force of gravity is said to be in a state of free fall. There are two important motion characteristics that are true of free-falling objects. Free-falling objects do not encounter air resistance when using these normal Newtonian calculations. All free-falling objects on Earth accelerate at a rate of 9.8 meters per second squared. Sometimes we can just say 10 meters per second squared for back of the envelope calculations, as it were. Because free-falling objects are accelerating towards the downward direction at a rate of 9.8 meters per second squared, if we made a dot diagram of the motion, it would depict an acceleration. The position of the object at regular time intervals, say every 0.1 second, can be shown. The fact that the distance that the object travels every interval of time is increasing is a sure sign that the ball is speeding up as it falls downward. Recall from earlier that if an object travels downward and speeds up, then its acceleration is downward. Remember that it still is accelerating even if it's negative. Free fall acceleration is often witnessed in a physics classroom by means of ever complicated types of machinery.
They use motion sensors connected to a computer program that outputs all the relevant data.
Tell them the way I would have done such experiments demonstrating the acceleration due to gravity on water droplets.
Okay. In a physics classroom, the room is darkened and a jug full of water is connected to a tube to a medicine dropper. The dropper drips water on the strobe, illuminating the falling droplets at a regular rate, say every 0.2 seconds. Instead of seeing a stream of water free-falling from the medicine dropper, several consecutive drops with increased separation are seen in the distance between dots. The pattern of drops resembles the dot diagram that we can create. There are other things we can get into, like kinematic equations. There are several of them that we need to use. We already saw the acceleration one and the velocity one, but we could go through a bunch of sample problems and solutions if we were in a class, but we went over the basic concepts in here. Kinematic equations and kinematic graphs are very important. But to finish the episode, what is the big misconception? The big misconception can be described as the following question. Doesn't a more massive object accelerate at a greater rate than a less massive object? In other words, wouldn't an elephant fall faster than a mouse? This is not true. They fall at the same rate.
I believe that is their Aristotelian way of thinking about gravity.
What is the big misconception, anyway?
The big misconception deals with how objects accelerate. The actual explanation of why all objects accelerate at the same rate involves the concept of force and mass. This is for free fall motion. The details can be discussed further if we get back into this subject at a later point in time. At this time, we can learn that the acceleration of an object is directly proportional to the force and inversely proportional to the mass. This is mechanics. We can get into mechanics at a later point in time, but I think we are getting pretty close to the end here where we need to come to a close.
I think that about wraps it up.
It's about time. I just want to get to my equations dealing with the communication.
In due time.
But for now, this is it for episode 45, Kinematics, part 2 of Quantum Foam. Alrighty, have a good one.
Quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.